All right, boys. Let's start. So this is the 2023 paper for science paper 2. Can you see? All right, let's quickly look at it and talk about it. What I want you to know is that when you're dealing with science, you should learn to separate bio, the physics, and the chem. Are we together? I want us to be able to separate the bio, the physics, the chem. Okay? Can you hear me? All right. Vic, can you hear me, Vic? All right. I want you to be able to separate the what? The bio, the physics, and the chem, okay? Those are very separate things. All right, good. So the bio is separate from the physics, it's separate from the chem. For bio, I mean, we have stage 8 and stage 9 together, they are coming. They are coming in the exam. Both things you did in stage 8 and things you did. But for stage 9, things that you did in bio are the photosynthesis, the bio part of science. Wait, sorry, let me fix this. Science has bio, physics, and chem. We know that. They call it science because it's a combination of these three. Bio is going to be photosynthesis, and not only photosynthesis, but we have photosynthesis, we have, you know, where you talk about excretion and transpiration, okay? Which I'll revise with you. Transpiration and excretion. This is also bio. Where for photosynthesis, we talked about photosynthesis and the carbon cycle, and then climate change. Then we have transpiration, excretion, and keeping a fetus healthy, where I told you the things that a fetus needs. Okay, I'll remind you. And then you have genes and you have inheritance. These are things to do with bio. Uh, in physics, what you have sound. Okay, you can deal with sound to talk about interference, to talk about the type of waves. So sound and waveforms, and then you also talk about forces, and we also talk about density. Do you remember us talking about density? All right, you talk about forces, you talk about density, you talk about energy. These things are the physics part of it. These things are the physics part of science. We know that it is the physics part. Then, of course, we have electricity. Okay, then you have other things which you would have covered at stage 8, other things. Then again, you have the chem part. In the chem part, you have rates of reaction. Rates of reaction. In the chem part, you have rates of reaction. In the chem part, you also have reactivity, where you talk about each group and its reactivity, and you talk about the reactivity series. Okay? Are you saying? Yes, yes. You have reactivity, then you have groups, you have properties of materials. This is chem. So when you're doing a science paper, you should see what question is it that you're struggling with, or what question should you go and here you can see it's genes. So obviously it's what? Which part has genes here? Genes are what? Are they in physics? No. Are they in chem? No. What are they in? Genes. Bio. So the whole of question number 1 will be bio. Each question is from something. So okay, this is bio. What about number 2? Can you see these? The periodic table and electronic structure. What is this? Periodic table. It's chem. It's chem. Well done. Right. Vic, let's go to the next one. This is your turn. Water moves through a plant, blah blah blah. They talk about the leaf, they talk about xylem, root, hair cell, the stem, xylem, things like this. Plants. Where do you talk about plants? What is this? Well done. This is bio. So we'd need to find the topic and we cover it. If it's in bio, it'll be in bio. Yes, that's good. And then what give me a second. Give me a second. All right, so now look at this. I'm happy you saw that this is bio. I'm happy. This is easy. This is easy. We move on. What about this now? Waveforms. Where do you talk about waves? I told you. And sound. What is this? This is physics. So if there's a chapter which we're struggling, we'll go to that chapter of waves and we'll polish up. What about the carbon cycle? The carbon cycle, it means with photosynthesis and these other things. What is this? It's not chem. It's bio. It's not chem. You can't talk about cycles in chem. The carbon cycle, this is biology. Well done. Then what about group 1 elements, melting points, radius elements, this, what is this? And trends, atomic whatever. These trends. What is this? Where do you do with groups? Do you do with groups in bio? It's obviously chemistry. All right, let's do this one. Mr. Vic, what about this one? What is it? Electrical symbols. This is physics, yes. What we do with electricity. Vic, what about this one again? Collision theory, and then for formation of the moon, they talk about density, dense rocks, whatever, collision. What is this? In here. Suggest why the density of the earth is greater than the density of the moon. Use ideas. Okay, when they say collision theory, there's a bit of chem. Chem is the one which talks about collision theory. So anyway, I'll help you with that. What about this? 1 million species. The word species and word plants. What is this? This is bio, where we deal with the word species and plants. And what about here when we deal with reactivity, going up or whatever? What is this, Vic? Where we deal with reactivity and the elements, calcium, zinc. What is this? This is chem. Well done. It's the one where you talk about these type of things. So when you're answering a question, you must quickly see which part. Is it the physics part? Is it the chem? Which subject is it? Okay. Here they want unit of temperature, decrease in temperature. Then improvements to an investigation. What is she doing here? Investigate which type of insulation is best. Transfer of energy. Where do you deal with energy? Which part? Which subject? Energy and the transfers. Physics. It's physics. Well then, thermal energy and the transfers. Here, dilute hydrochloric acid. Once you talk about hydrochloric acid, these acids, it's chem. It cannot be biophysics. Well done. Anyway, so this is what we'll do. So we are going to use this paper. We'll analyze a lot of the questions. We'll do the ones to do with chem, the ones to do with bio. What I want to just quickly give you is a lot of information and data. Are you ready? Today we are doing chem part and we are doing chapter 8. 8 for stage 9. Checkpoint science. We can just say it has nine topics. And we are doing topic number 8. Which is called rate of reaction. Quickly write rate of reaction and let's move. Quickly write this. Did you write rates of reaction? Now I want you to write here to say a reaction usually does not happen in one instance. To say quickly, the reaction is done and the whole reaction is complete. That's not how it happens. That's not what happens with reactions. So when we are studying a rate of reaction, you must know that we don't just say, oh, the reaction has happened, it's finished instantly. No. Some reactions are fast, but some are not. So some reactions are, one, very fast. Some reactions are very fast, and those are the explosions. Then some reactions are medium. Some reactions are medium speed. For example, burning fuel. It's not an explosion, but when you burn firewood or whatever, it's going to be a medium speed reaction. It's not too slow. Then some reactions are very slow. We can have a reaction which is very slow, okay? E.g., rusting. So you must know that reactions don't happen at the same speed. Some are very fast, some are just okay, some are very slow. Are we together? Good. So this topic which you'll be doing, which is rate of reaction, what must you know then? I want you to write now to say the rate of reaction tells us how fast reactants are being used up, or how fast products are being formed. Rate of reaction tells us how fast reactants get used up or how fast products get formed. Are we together? How fast is a product being formed? So talk about one. If you want to talk about the rate of reaction, choose one. Are you going to use the reactant? If you're going to use the reactant, then you're going to say the rate of reaction is how fast a reactant is used up. Are we together? If we're going to use a product, then the rate of reaction is how fast a product is formed. You look at a product, you see how fast it is being formed, then so it's the amount of product that is formed per unit time. So there is time involved here. How fast the product is formed will be the rate of reaction. So use what you want to use, but choose one. How fast the reactant is being used up, or how fast products are being formed. Are we together? So if we say rate of reaction, so if we say rate of reaction, you say the amount of reactants used up in a given time, or the amount of product formed in a given time. This can tell us the rate of reaction. So if we say rate, rate of reaction is equal to amount of reactant, or you can even say amount of product formed divided by time. Can you see this? Are you sure? Good. So rate of reaction, you choose one. Here for the formula we use product. Okay, or the amount of reactant used up over time. Are we together? Have you written this down? Are you sure? All right. Let's see here. At the beginning of a reaction, there are lots lots of reactants. Both reactants. Or lots of reactant particles. I wanted to say particles of reactants. This is at the beginning of the reaction. Now, what you must know is that, so you can say, therefore, many collisions. Okay. Then you say, as the reaction continues, reactants are used up. As the reaction continues, the reactants start to get used up and are used up, and fewer particles here. Reactants are used up and fewer particles remain. Therefore, I want you to say, therefore, fewer collisions. Okay. Therefore, fewer collisions remain. Now I want you to say, and the rate decreases. Have you seen this? It's all about the number of particles and the collisions. At the beginning, you have a lot of particles. So at the beginning of the reaction, you have lots of it's about number of particles. I want to hear. You have lots of reactants, which means you have a lot of particles. And you have many collisions, like here. Let's just say we have a situation like this. Here are our reactants. These ones are going there, these ones are going there. They'll bump into each other, collide, and you're going to have a very fast reaction. Now, so the rate is very high. Now, as the reaction continues, your reactants are used up, and you have fewer particles, and that means fewer collisions, and that's it. Are we together? So it's about the number of particles and how they affect the number of collisions. Do you hear me? What is the rate of reaction? The amount of reactant used up in a given time. What about another way to say rate, to define rate of reaction, Vic? Yes. The amount of product formed in a given time. Huh? Is it going to be the same throughout the whole reaction? What is going to make it change? And tell me how it changes. The rate of reaction. It's not going to be the same, yes? How does it change? At the beginning of a reaction, the rate is high, right? Because why? There are a lot of reactant particles. Are we together? Well, there's a lot, so at the beginning of the reaction, there's a lot. But as the reaction progresses, what do you have? The particles, the reactant particles reduce in number, so there are fewer collisions, right? Fewer collisions will remain. Have you seen this? Now I'm going to do a small diagram. How to measure the rate of reaction. How to measure the rate of reaction. Scientists measure the volume of gas produced as a way to measure how fast the reaction the reaction is. Let me say occurring. Are we together? The volume of gas produced. You can I want you to write here. You can measure the volume of gas produced Should I now give you the apparatus? What are we measuring? The volume of gas produced in a reaction. Right? So this reaction clearly produces a gas. And we want to measure the volume of it produced. And it will give us the rate of reaction. All right. Let's do it. Let me fix here. Say the apparatus required, the equipment, right? 4 things. 1, let me write it nicely. Sorry for the pen. Conical flask. Say conical flask, then say magnesium ribbon. Yes. Magnesium ribbon. Then 3 is sulfuric acid. Then 4 is a gas syringe. So you need a conical flask, magnesium, sulfuric acid, and gas syringe. Right. If I put the apparatus like this, and I put them like this, 4 things. Are we together? Have you seen the 4 things that we need to carry out this experiment? Students, are you seeing? And I want you to know the conical flask. Look there. Um, I want you to say here. Did you write to say conical flask? This is a conical flask. Okay? Then you need magnesium, ribbon, sulfuric acid, and gas syringe. Right. This is the apparatus. Now let me give you what you need. The other things, right? Hello? Okay. Should I put what actually happens? If we put the steps like this, I'm trying to put them. Hydrogen gas forms when magnesium reacts with sulfuric acid. Hydrogen gas forms, right? So you'll be doing it like this, then you collect it in a syringe. So you collect it like this. Okay, you should find a way to connect your syringe with this. Are we together with the conical flask? So you need a collecting. Then this is the syringe, okay? So initially the syringe, you put the slider here. Are we together? AT. There we go. Then it's going to be pushed backwards this in your syringe. It's going to be pushed backwards because you're going to have hydrogen gas going in like this. So the hydrogen gas pushes the syringe plunger outwards. The longer the time, the more the plunger is pushed. You can say the more the hydrogen produced, and then likewise the more the plunger is pushed backwards. The more the plunger is pushed backwards. So we can be reading values and we wait every 30 seconds, 30 seconds, 30 seconds. We see where is it now, where is it now? Okay? So you can measure by reading the scale. We can measure, guys, we can measure one, gas volume after 30 seconds. Two, gas volume. How do we see the gas volume? Where the plunger is. Right, guys? This syringe is being pushed outwards. So we'll be seeing now where the plunger would be. Right? We will now see gas volume after 60 seconds. Then again, we will now see gas volume after 90 seconds. So we'll be just seeing the gas volume and we'll be measuring. we'll be using that to measure the volume of the gas produced. Do you have a question? Do you see this? Hello? Do you have it? So let's put example of experimental results so that you now see how we then use to measure the rate of reaction. Example. Pardon? Okay. Example, experimental results. Let me go up a bit so that you see what you want to see. Let's see. You have written? Are you up to date? Now let's move. So let's put example of experimental. Here's a table which you'll be writing. You'll be looking at the time nicely, very fast. Okay? You'll be looking at the time. And you'll be looking at the volume of hydrogen. Hydrogen volume. How do you see the hydrogen volume? You look at the syringe. You look at the syringe. Where is the syringe at? This one, the plunger. 0 is here. This is where it is 0. Then it starts moving backwards and the volume is increasing. The volume of hydrogen in here. Can you see? Vic, are you seeing this? Yes, you put magnesium, a metal, with an acid, you get hydrogen. We're actually doing it with the people who are a little bit older than you guys yesterday, seeing what happens. So this would be magnesium ribbons. Then this is dilute. It has to be a dilute sulfuric acid. You are mixing. There is the dilute acid and whatever. Then here you get hydrogen gas coming out. This is hydrogen. This container is the conical flask. Have you seen what a conical flask looks like? This is the conical flask. So now we say time 0 seconds, time 30 seconds, time 60 seconds, time 90 seconds, time 120, time 150, time 180. Yes? Pardon? Hydrogen forms when you add a metal to an acid. Okay, magnesium, which is the metal, is added to dilute acid. Are we together? You form hydrogen gas. You form hydrogen gas. These are the bubbles, so they start to come out. And that hydrogen gas, which is being formed, is going and pushing the syringe backwards. So that's the volume you are measuring. It's the volume of hydrogen. Because when you add a metal to a dilute acid, you are going to get hydrogen. Don't worry about that. It's going to happen. So we've added our magnesium, which is obviously a metal. I showed you where you find metals in the periodic table. I showed you guys. So you add your magnesium strips, add to hydrogen, add to dilute acid, to your dilute stuff. Then hydrogen is being formed, it goes there. And I want you to be looking, you have your timer. So you also need a timer. This is a syringe. Are you seeing? You obviously need a pen and a paper to be recording. So you start the timer. You add your magnesium. The moment you add your magnesium, you start the timer. Then you'll be looking at the syringe to see how much hydrogen has gone into the syringe. So of course at the beginning there is nothing. There is no hydrogen in the syringe. After 30 seconds, you may see that the syringe has moved by 10 cubic centimeters. You see, after 60 seconds, you see, it is now at 20. After 90, where is it now? Oh, it's now at 26. After 120, it's now at 40. After 150, it's now at 48. After 180, it's now at 54. This is an example. So this is example experimental results. So time, then here it is the hydrogen volume. Are we together? You can keep it running. Okay, you can keep it running until it gets stationary. Don't stop it right now. Let's push it. Let's get it. We say 210, then we say 240, then we say after every 30 seconds we are checking. Then after 300 seconds, then after 330 seconds, you are just checking it. Then maybe it will become stationary here at 330. It will be 66, here 66, here 66. Stays. That's when you see to say, okay, maybe let's say here 60, then here 64. So when you see it being 66, 66, 66, the syringe is no longer moving, so reaction is stopped. Okay. You can say here, syringe is no longer moving, which obviously means reaction has stopped. No more hydrogen is being produced, so obviously the reaction has stopped. Are we together? So what can you say here? At first, from 0 to 10 seconds, from 0 to 30 seconds here, it improved from 0 to 10. That means there was a huge increase, right? So here, volume of gas increases quickly. And I'm going to show you how you can see it through calculations. But look now here, look here. 60 to 64. Volume of gas increases more slowly. Here you can actually see that from 40 to 48, it has reduced, or 48 to 54. You can see volume of gas increases slowly. Then there it's actually more slowly from 60 to 64 in 30 seconds. This is still 30 seconds. This is still here 150 to 180. This is still 30 seconds. This is still 30 seconds. So in these 30 seconds from 0 to 30, it increased by 10. Here 150 to 180, it increased by 6. Then here 210 to 240, it increased by 4. Then here 270 and whatever, it is no longer increasing. So at first it increased by 10, then it increased by 6, then it increased by 4, then it stopped increasing. So the increase is becoming slower and slower, which means reaction is slowing down. Do you understand this? Reaction is slowing down. That means the rate is decreasing. You understand? Are we surprised that this is happening? No. We expected, right? We said what should happen in a reaction. At the beginning, we have a lot of reactants. There's a lot of reactants. There's a lot of reactant particles. So there are many collisions. So the rate or the speed of reaction is very high. Then as the reaction progresses, the reactants are reacting and reducing in quantity. So there are less reactant particles and the rate decreases until the reactant particles are finished and the reaction stops. So that when the volume stops increasing, it is where you have this 66 cubic remaining at 66. The volume is no longer increasing. The syringe is no longer moving. The reaction has stopped. So, why doesn't the gas keep increasing? The volume of the gas being collected. Why doesn't the hydrogen volume, in this case, or you can say gas volume, being produced does not increase forever? Because at some point, one of the reactants becomes used up. At some point, one of the reactants becomes used up. Okay? Here you can say, e.g., magnesium or the acid. One of them will become, so the reaction will stop. Are we together? Now, there can sometimes be an anomalous result in the values, in the volumes recorded. Sometimes you can get an anomalous result. Okay? Anomalous result. I'm giving you a heads up. Vic, are you seeing? An anomalous result. Victorson, are you seeing this? I mean Vic. Where is Vic? I'm talking to Vic. Vic, are you seeing this? All right, so I was saying an anomalous result. We sometimes can get an anomalous result in the table. Are we together? An anomalous result is what? A result that does not fit the pattern. A result that does not fit the pattern. A result that will act as if the volume is actually increasing more, so the reaction is actually moving faster as time is moving. A strange value. An anomalous result. A value that does not fit the pattern or follow the trend. A value which does not follow the trend. In other words, we are saying a strange value. Let's just say that you had a value here which is like at some point you get 85. Then you start getting 64, whatever. A very big value. Look here. Yeah, you can get a very big value. What will be the reason? Yeah? What reason is that? An anomalous result. Sometimes there can be an anomalous result. They can ask you reasons for anomalous results, values that don't fit the trend. Are we together? Reasons for that would be one, a reading mistake. If you do a reading mistake, you're going to get a value which doesn't fit the trend. Number two, a timing mistake. If you do a timing mistake, you get a value which does not fit the trend. Number three, an equipment problem. An equipment problem. If you have a problem with the equipment, you get a value which does not fit the trend. Are we together? Number four, human error. If there is human error somewhere, you get a value which does not fit the trend. Yeah? Are we together? Are we together? All right. Good. So now you can be calculating the rate of reaction. If you want to get the rate of reaction, first you can do the graph from this. You measure the graph. You create a graph, then you're going to check the gradient of that graph. Then you have the rate of reaction. Are you seeing all this? Hmm? So this would help you to get what we call the average rate. So here's what you're going to do. Huh? You can use a graph. So I want you to say, okay, we can get an anomalous result. It can be because of a reading mistake or a timing mistake or some equipment problem or some other human error. Another human error. Now, here I'm saying you can now say, how can I then use graphs? How can I then use graphs to measure reaction rate? How can I then use graphs to measure reaction rate? How can I then use graphs to measure reaction rate? What time do you guys want to go for tennis? All right, good. Good, good, good. Using graphs to measure reaction rate. That's good. Let's see. How then do we use graphs? A graph is the easiest thing. The x-axis of the graph is always time. Time is always on the x-axis. And then the y-axis is going to be volume. It's going to be volume produced. The y-axis is the volume of the gas that is produced. The volume of gas. You can just say volume of gas. Okay? You can just say the volume of gas. Are you saying? Are you seeing? Yes. You can put it like this. You get the volume of the gas produced, and then always put time on the x-axis. Don't let me down. Always put time on the x-axis. Now, the gradient is the one that will tell us the slope, the rate of reaction. Okay? So, the gradient of this, gradient means what? The slope of the line. The gradient or the slope. Okay? Tells us the rate. How fast the reaction is happening. Or we can say the gradient tells us the rate. The rate of reaction. Okay, if you have a steep like this, steep slope, this means reaction is fast. What about if you have a gentle slope? Gentle slope, it means reaction is slow. Are we together? And then if you get a horizontal line, if it's now flat, I don't know why this thing is fighting, eh? Okay, I'm gonna go up. Wait. Like this. You want to see here? The x-axis. The x-axis is always time. Anytime you do. Okay, the next page. Okay. But I was saying like this. Anytime you do a graph, time is always put on the x-axis. That's not even. Here you put now the volume of gas. Yes, I've gone up. You want to see this? Okay, the gradient tells you how fast. So if you want to, we say the gradient tells you the rate of reaction. You just look at the slope. Just look at the slope and you know the rate of reaction. Is it steep? Like, can you run up that slope? Or you can't. If it's so steep you can't run up that means that reaction is a very fast one, actually. That's a very fast reaction. Once you see it being flat, the more flat it gets, the slower that reaction. We are not going to celebrate a flat slope. Come on now. A flat line, horizontal line or flat line, that means the reaction has stopped. Once it gets to this, it means reaction has stopped, guys. Once it gets to this level, it means the reaction has stopped. So you can, okay, you can stop your timer. Okay? Are we together? Right. Now, the last thing is, when you are now doing calculation, I want you to say, you should know the average rate of reaction. You get it by now saying here. You check the amount of product formed at any given point in time divided by the time. Are we together? Then we'll be seeing the rate of reaction at that particular thing. Are we together? Yes. So what you must know is that we already explained to you why. We already explained to you why. We already explained to you why reactions slow down. I said, why do reactions slow down? Why reactions slow down? Why do we have reactions slowing down over time? Tell me, why do reactions slow down? Number one, because the reactants get used up, right? Reactions slow down with time because reactants get used up. Or you can say reactant particles number decreases. The number of reactant particles decreases. if the number of reactant particles decreases, the collision frequency decreases, the number of collisions decreases, and now the rate then decreases. The rate then decreases. Are we together? Are we together? Okay. Reactant particles number decreases. The collision frequency decreases, then the rate will decrease. Okay, when there are less particles, there will be less collisions, the rate will decrease. You're not going to forget these. No. Come on now. Okay? Should I give you questions that you must know? Should I give you some main exam questions? Main exam questions to know. Main exam questions to know. Okay, from this section. Number 1, we'll do the solution. Define rate of reaction. Huh? Are you ready? This is just, we are just doing the first part of chapter 8. All right, so number 1, they can say define rate of reaction. Define rate of reaction. Then, what do we say? Okay, let me just list for you the important questions. Okay, the main questions. Right? Let's say number 1, define rate of reaction. Then I'll just give you a few questions. Let me think. Few questions. 2, explain why a reaction slows down. You know the 3 points to say. Okay? Just gonna give you. Then you can say 3. Explain why a graph becomes horizontal. Explain why a graph becomes horizontal. Number 4, identify an anomalous result. Identify an anomalous result. Number 5, calculate average rate from a graph. These are examples of important questions you can get. Right? Are you seeing examples? Explain what a steep gradient means. Number 7, are you seeing? Huh? Are you seeing 80? Vic, are you seeing? Vic? Where is Vic? Vic? Are you writing these questions? Are you writing? Huh? Look at these. Explain how a explain what a shallow gradient means, and then how a gas spring measures. Right. Let me do the solutions with you guys. For things that we can write. Number one, solutions. Solutions say number one, define rate of reaction. This is the easy. Amount of reactant used up. Or you can say the amount of product formed in a given time. So the amount of reactant used up in a given time. Are we together? Or the amount of product produced in a given time. 2. Explain why a reaction slows down. Right? Are you saying this? This is the second question. Please tell us with time. Please tell us. Can you explain why a reaction slows down? This is the second question. Explain why a reaction slows down. Here. I want you to say, as the reaction slows down, or as the reaction proceeds, reactants are used up. This means there are fewer particles. You should say fewer reactant particles. If you don't talk about fewer reactant particles, then I'm not happy. To collide, then you should talk about less collisions, fewer reactant particles to collide. So the frequency of successful collisions decreases. And the rate of reaction slows down. Are we together? Do it. Should we do the next one? Number 3. What did it say? Explain why a graph becomes horizontal. Because the reaction is finished. How easy is that? A graph becomes horizontal because the reaction has finished. Due to one of the products or one of the reactants, due to one of the reactants having been completely finished or completely used up. So no more product is produced. No more product is produced or is formed. No more product is formed. So if they say number 4 now, identify an anomalous result, you will just look for a result which doesn't follow the trend. And I want you to then write to say the result at, then you put the time, then you say is anomalous. You tell us. And you say because it does not follow the general trend. The general trend, okay, shown by other results. Shown by other results. An anomalous result does not follow the trend or the pattern, so therefore it is anomalous. Here, calculate average rate from a graph. From a graph, you see the amount of time that it takes to produce something, then you divide. So average rate, I'll do examples. Average rate is equal to amount of product formed divided by time taken. Is the amount of product formed divided by the time taken. This gives us the average rate. Then we do number 6. Explain what a steep gradient means. Amount of product formed divided by the time taken. Yes. Okay. Explain what a steep gradient means. A steep gradient means, so what is it? Explain what a steep gradient means. Yes. A steep gradient means the rate is fast. So you can say the reaction is occurring at a fast rate. Then number 7. Explain what a shallow gradient means. Number 7. A shallow gradient means the reaction is occurring at a slow rate. It's moving at snail pace. That is why you just have a gradient like this. Yuck. All right. Describe how a syringe measures rate. We should describe. How does a syringe measure the rate? We just did it. The gas produced during the reaction enters the gas syringe and pushes an important thing called the plunger. Pushes the plunger outwards. So the gas that is produced in this reaction could be going and entering the syringe and pushes the plunger outwards. Then you can say the volume of gas produced is measured at regular intervals. Like at every 30 seconds, you're looking, where is the gas now? Where's the volume? Where's the volume? Okay? Now you should say the rate of reaction is determined from the volume of gas produced over time. The volume of gas produced over time determines the rate. This is it. These are the 8. These are the 8 solutions. Have you seen them? Oh, so what is left is for me to give you a few questions. And I'm going to see how you guys are going to do. Want to see how you guys are going to do. Few questions from this, then we'll do the next part, obviously. I'm also doing lessons with Alex in the evening. He calls me. I think you people should also call me, right? So you should call me at around, whatever time you can, and you do something else. You can also do that, okay, guys? Yeah. What time do you normally go to bed?